Our next speaker is James Sowers from Minnesota Duluth, who will speak, of course, on partitions.
Thanks, Mel. Thank you very much. And yeah, let's go ahead and get started. So the title of my talk is Sequentially Congruent Partitions and Partitions into Squares. I'll explain what all of that means in the talk. So no worries if some of those phrases don't make sense yet. So let me begin by thanking Mel for the opportunity to share this talk today. I wish I could actually be in the same room with Mel and the rest of the participants, but at least we can do this. So Mel, thanks for the opportunity. And let me also say thanks to Robert Schneider and Ian Wagner for a very fruitful collaboration. I'll share the details of that collaboration later in this talk. So my goals are pretty straightforward today. I want to start by discussing the work of Schneider and Schneider, the father-son team of Robert and Max Schneider. And in doing so, I want to introduce the concept of sequentially congruent partitions, which they defined in their work a couple of years ago. And then to close out the talk, I'll talk about work of Robert Schneider, myself, and Ian Wagner, which extends this work that Robert and Max did and incorporates, brings in partitions where all of the parts have to be squares, which is a beautiful combinatorial issue that arises in the work. Okay, so let's begin with some notation and some definitions just to make sure we're all on the same page. I'm going to let this capital calligraphic P denote the set of all integer partitions of all weights, including the empty partition. And I will let that same P with the subscript N denote the set of partitions whose weight is N. So the sum of the parts of those partitions is exactly the positive integer N. And so we're going to let little p of N be the function that counts the number of partitions that are inside capital P sub N. In other words, the number of partitions of weight N. This is the usual unrestricted partition function. We're going to write an arbitrary partition lambda with its parts just in parentheses with commas separating them. And the largest part will be first, and then the parts will descend or non-increase as we read left to right. All the parts have to be at least 1. We're going to let little l of this partition lambda, which is simply this r, this subscript r, it's going to denote the number of parts or the length of the partition, L for length. And we're going to let the norm of lambda, the absolute value of lambda, basically it's simply the weight of lambda. It's going to be the sum of the parts in the partition lambda, lambda 1 plus lambda 2 up to lambda r, all summed together. That's going to be the norm of lambda. And we'll worry about length and number of parts and weight of partitions throughout the talk. So we're going to want to be very clear about what parameter it is we're studying as we go. So there's another way to write a partition, which goes back several decades. It's known as the frequency notation for a partition. And so in that case, we're going to write our partition lambda again with parts inside parentheses, but now no commas. And we'll have a 1 with a superscript M1, a 2 with a superscript M2, and so on. And the superscripts will be the frequencies or the multiplicities of the parts. So if you have an I with a superscript M sub I, it means that the part I appears in lambda exactly M sub I times. And this frequency notation will be central to us later in the talk. So next, I need to provide the definition for sequentially congruent partitions. For many of you, what I've just said might be fairly well known. You might be familiar with it. I'm going to guess, though, that for most of us, the next definition is less known. And so we're going to chat about it for a moment and include an example as well. So here's the the definition around which a lot of this talk revolves. We're going to say a partition lambda is sequentially congruent if the following set of congruences hold. So the first part, lambda 1, has to be congruent to lambda 2 mod 1. This is a trivial congruence. This is always true no matter what lambda 1 and lambda 2 are. Lambda 2 needs to be congruent to lambda 3 mod 2. Lambda 3's got to be congruent to lambda 4 mod 3. In other words, lambda I has to be congruent to lambda I plus 1 mod I for all the i's up to r minus 1. So as we get close to the end of the partition, lambda sub r minus 1 is congruent to lambda r mod r minus 1. And the last part, lambda r, needs to be congruent to 0 mod r. And I would like to suggest that this last piece of the definition is very natural if you simply imagine appending an infinite sequence of zeros to the end of the partition lambda. So you'd have lambda 1, lambda 2, lambda 3, dot, 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 lambda r, 0, 0, 0, 0, 0, 0, 0. And then this last piece of the definition makes perfect sense. And of course, if you had all zeros after that, then what you might imagine being all of the congruences afterwards, they would all be trivially true. So this is the definition of a partition being sequentially congruent. You must have the sequence of congruences hold as you take the parts in sequential pairs. So let me give you a quick example. I claim that the partition 20, 17, 15, 9, 5, that this is sequentially congruent. Let's just talk it through quickly. 20 is congruent to 17 mod 1. Again, that's trivial. 17 is congruent to 15 mod 2 because 17 minus 15 is 2. 15 is congruent to 9 mod 3. 15 minus 9 is 6. That's divisible by 3. 9 is congruent to 5 mod 4. And lastly, the 5 is congruent to 0 mod 5 because 5 is a multiple of 5. So this is a sequentially congruent partition. The next example, I just want to add 1 to every one of the parts in the previous example. And by adding the same number across all of the parts, it turns out that all of the first several congruences must still hold for the same reasons that they held before. However, when you get to the end, now you're asking, is 6 congruent to 0 modulo the number of parts, which is still 5 in this case. And of course, 6 is not divisible by 5. And therefore, this new partition that starts with 21 is not sequentially congruent. Now, with that said, if you think about it for a moment, if I go back to the first example on the screen that starts with a 20, if I had added to every one of the parts the same multiple of 5, let's say I had added 5 to all the parts so that I ended up with 25, 22, 20, 14, and 10, then that would have also been a sequentially congruent partition. And I could have kept doing that as long as I wanted. So we could certainly have done this addition, a trick or method to build new sequentially congruent partitions pretty easily. I just needed to make sure I added multiples of 5 rather than simply adding 1 like I did in this second example. So I'm going to let this calligraphic S, which is a subset of P, I'm going to let it be the set of all sequentially congruent partitions, regardless of weight or any other parameter. And I'm going to let capital S sub LG equals N be the subset of S, which is the set of sequentially congruent partitions whose largest part is equal to N. So for example, this first partition on the screen would have been, is an element of S sub LG equals 20. The largest part, N, would be 20 in that case. So notice that if you increase the largest part as much as you want in a partition that's sequentially congruent, then you're going to yield another partition which is sequentially congruent because the first congruence in the definition is the only one that involves lambda 1. And of course, all you're checking is that lambda 1 is congruent to lambda 2 mod 1, which is trivially true. So I could increase the first part as much as I want and still end up with a partition in S. Of course, that new partition would be in a different set of the form S sub LG equals whatever. It would be in a new set of that form. But if I'm looking at S as a whole, the new partition would be in S. And again, as I said a moment ago, if you add or subtract a fixed multiple of R to all of the parts in a partition in S, then you'll get another partition in S, as long as the resulting parts are still positive. So here I'm speaking mainly to the idea that if I subtract too many copies of R away from all of the parts, then of course some of the parts are actually going to go negative. I won't have a partition in that case. So, but if I want to add multiples of R, positive integer multiples of R, I can do that all day, and I will stay inside capital S in the process. So for those of you who have done anything with integer partitions, you might wonder whether these sequentially congruent partitions fit at all naturally in the theory of partitions. I'm going to be really honest and tell you the first time I saw them, when I saw Robert Schneider speak about these, my first inclination was that they seemed a bit contrived or a bit odd. But my hope is to answer for you today that they really do fit in a very interesting and natural way in the theory of partitions. And so if we look at the work of Robert and Max Schneider, which appeared in the Annals of Combinatorics in 2019, we see that these sequentially congruent partitions really do fit very nicely in the theory of partitions. So let me start to try to convince you of that with the following theorem from their paper in 2019. The statement of the theorem is that there's a bijection, pi, between the set of ordinary unrestricted partitions and the set of sequentially congruent partitions, such that if you map all of the, you can map in bijection all of the partitions of weight n, unrestricted partitions of weight n, to the set of partitions which are sequentially congruent, where the largest part is equal to n. So I'm going to show you the proof of that in just a moment. It's a constructive proof. But let me point out then a quick corollary, which is that the size of the set S sub LG equals n must equal little p of n, because we know that the size of capital P sub n is little p of n. So here we have a new set of partitions, all of which have largest part equal to n, and they are sequentially congruent. And that set of partitions is also has size little p of n. So let me give you the proof that Robert and Max showed to prove that this bijection exists. So I'm going to start with a partition lambda. This is an unrestricted partition in the sense of the parts. The only key is that it has to have weight n. So the sum of the parts is n, which means this partition lives in capital P sub n. And we know nothing else about the relationship of the parts to each other. And now I'm going to construct a sequentially congruent partition, lambda prime. And the main formula for this is that each part, lambda I prime, is going to equal I times lambda I from the previous partition, plus the sum of the remaining parts inside that original partition, lambda. Now we need to check a few things. We need to check all of those congruence properties, and this partition needs to live inside S sub little LG equals little n, LG equals n. So the largest part needs to be of size n. So let's go through that process. First, the last congruence in the sequentially congruent definition is that the last part, in this case lambda r prime, needs to be divisible by r. Well, if you think about it for a moment, if I is equal to r, this sum at the end is actually going to be empty. So lambda r prime is just going to be r times lambda r. Well, I don't know anything about lambda r, but because there's an r that's going to be sitting in front of it, I know that I have lambda r prime is divisible by r. So that last congruence is settled. And all of the other congruences are going to follow because lambda I prime minus lambda I plus 1 prime is equal to I times the difference of the corresponding original parts. And this I that's sitting in front on the right-hand side is going to give you the congruence mod I that you want. So all of the congruences hold, which is lovely. And then all you have to check is that the largest part, lambda 1 prime, is equal to n. But lambda 1 prime is 1 times lambda 1 plus the sum of all the other parts in the original partition. And that is just the sum of all the parts in the original partition. And that, of course, is n because the original partition had weight n. So the largest part here is equal to n, which means we've shown that lambda prime is an element of capital S of little g equals n. So I've got this function which is now mapping me from P sub n over to the right sequentially congruent partitions. And this map is easily invertible, and that completes the proof. So we have this gorgeous construction to show a bijection between ordinary partitions of weight n and these sequentially congruent partitions with largest part equal to n. And I'll just note very quickly that Robert and Max in their paper proved that there's a generating function argument here as well. I won't go into it today, but it's a really pretty argument. For those of you interested, you might want to check that generating function argument out as well. Okay, so the two Schneiders also showed an interesting connection between sequentially congruent partitions and what they called frequency congruent partitions. So let me define those quickly. A partition is frequency congruent if it has the property that each part divides its frequency, which serves as the superscript in frequency notation. So if every part divides its own frequency, then you have something called a frequency congruent partition. I'm going to let capital L be the set of all those partitions, and I'm going to let capital F sub little l equals n be the set of frequency congruent partitions of length n, so that the number of parts is equal to n. And Max and Robert proved that for each n, this set of sequentially congruent partitions with the largest part equal to n is the same set as of the same size, I should say, as the set of, no, I'm sorry, they proved that the two sets that I've shown here are equal, that the set of sequentially congruent partitions with largest part equal to n is the set of frequency congruent partitions with length equal to n. And the proof of this result is simply partition conjugation. So if you've written a partition in a Ferrer's graph or a Young diagram, and you simply take the main diagonal of that and flip the partition over that main diagonal, you go between these two sets. And of course, length equal to n, largest part equal to n simply tells you what's happening in the top row, and length equal to n tells you what's happening along that first column. And so the conjugation is flipping largest part equal to n and length equal to n, and simultaneously it flips the sequential congruentness and the frequency congruentness as well. So for example, I told you that 20, 17, 15, 9, 5 is in the set S sub LG equals 20. It's got largest part 20. When you conjugate that partition, you get 3 1s, 2 2s, 6 3s, 4 4s, and 5 5s. And you can see that each part divides its frequency, which is the superscript. And if you add the superscripts, you get exactly 20. So you have exactly 20 parts, or length equals 20. And so you're living, the new partition lives inside this set. And of course, the corollary means that capital F sub little l equals n is equal to P of n as well in cardinality. All right, so in March 2019, I saw Robert give a talk on this topic at an AMS conference in Auburn. And I noticed something, which was that this little n was serving as a parameter for lots of other reasons, largest part, number of parts, and it didn't serve as the weight of the partitions. And it seemed natural to me to ask the question, what's happening to the number of sequentially congruent partitions of weight n? in some sense, my partition upbringing sort of led me back to thinking about the weight of these partitions rather than the size or number of partitions. And so after Robert's talk, I went and calculated the number of these sequentially congruent partitions of weight in. I punched that data into Neil Sloan's online encyclopedia of integer sequences, and I was thrilled with what it told me, it conjectured, and I shared that information with Robert, and he and Ian and I began working together. And in the process of working together, we proved a really cool result. And let me just share that result with you in closing today. So I'm going to let little p sub s of n be the number of sequentially congruent partitions of weight n. That's different than what we've been talking about earlier. And little p sub f of n be the number of frequency congruent partitions of weight n. And then p sub square of n is going to be the number of partitions of weight n where all of the parts are squares. So we restrict very heavily the parts that are allowed in p sub square of n. And it turns out that for each n greater than or equal to 1, all three of these functions are equal to each other for the same weight n. This is a really cool result, and it's really fun to see this p sub square function showing up. And so let me just show you a quick proof of this result, which I think is very pretty from a combinatorial standpoint. So we know the p sub s of n and p sub f of n are equal because conjugation is a weight preserving map. So that equality, the first equality here, is actually very, very easy. So all I want to do now is prove that p sub f of n is equal to p sub square of n, and I'll do it by construction. So I'm going to start with a partition which is frequency congruent. So it's being counted by p sub f of n. It has weight n. I'm going to call that lambda star. That means that every part in that partition divides its frequency. So that means I can write p sub star in frequency notation and explicitly put a copy of the size of each part in the frequency superscript. And that's what I've done here. So lambda star can be represented this way. And now what I want to do is just understand what I'm going to do. Well, what I'm going to do is replace each part of the form I superscript I times E sub I with I squared superscript EI. Now, clearly, this partition is a partition into squares. So there's no question that I've mapped from the right two sets. The only question is this new thing on the screen a partition of weight n? That's the important part. Well, let's go back to this part, I with superscript I times EI, and ask ourselves, what is the contribution of that term? Well, it's going to be basically the part I repeated I times EI times, and the weight of that is the same as I times that same sum, just EI times. You can think through that for just a moment. And if you distribute those i's, that I, into the parentheses, it's the same as the weight of I squared EI times, which is what you have here. And if I do that across all of the parts I in the original partition I started with, then I'm going to end up with the same weight here, and that is n. And therefore, this new partition is of weight n, and it's going from the right set to the right set. And this map is easily invertible, and therefore I have a bijection. And so p sub f of n is equal to p square of n. Let me show you a quick example that I really like. Start with this sequentially congruent partition. I promise you it's sequentially congruent. I'm going to take its conjugate and get this frequency congruent partition. And again, each part divides its frequency. And now I'm going to do the map that I just showed you. And when you do that, 1 appears twice, 4 appears 3 times, 16 appears twice, 25 appears once. And this, of course, is in the right set, the partitions in the squares. But I think the important thing is to realize what happens from the top here to the bottom if you write these in Fourier's graphs or Young diagrams. This is the Young diagram if you ignore the gray boxes for 21 in the first row, 19 in the second row, 13, 13, and 5. So this sequentially congruent partition is just a regular Young diagram. And if you block these off in the right way, here's a 25, which is here. There's a 16 with another 16. There's the two 16s. There's a 4, and a 4. Those are the 3 4s. And a 1 and a 1. Those are the 2 1s. So you can see from the picture, if you will, how to get from the sequentially congruent partitions to the partitions into squares. And I'll just mention that we expanded this from squares to partitions that were powers, or that were not just squares, but had exponents of the form k+1. This paper's been accepted and will appear in the Ramanujan Journal at some time in the near future. And since I'm low on time, I'll close there, and thank you very much.
Oh, thank you, James. It was lovely. Any questions for our speaker? So I have a question, which is, I mean, so absolutely lovely talk, but walking down the street, looking up at the sky and the clouds, would anyone ever think of these sequentially congruent partitions? I mean, where do they come from? I mean, you've shown how they're bijectively interesting, but why would you look for this or find this in the first place?
Mel, it's a great question. And my quick answer, so that we stay on time, is to go back to Schneider and Schneider from 2019. I think they're the ones who really came up with it. Where they came up with it was going back to Euler's original statement from the generating function for P of n, right? So you have the product 1 over 1 minus q to the n. In the middle of that equality, it's very natural to write down this m-fold sum that represents that infinite product. And if you think about a moment, what's going on in that m-fold sum, it turns out that what's being counted are these sequentially congruent partitions. So they're hiding inside that representation that goes all the way back to Euler. But beyond that, walking down the street, looking up at the sky, you're probably not going to come up with these partitions.